Here we talked about curvilinear particle motion and projectile particle motion. Please note that this is just motion for particles, not rigid body yet, so we don't need to consider rotational motion. Let's look at this coordinate system. This is my x coordinate and this is my y coordinate system. And then just imagine that a object just follow through curved path. So this is a particle, no rotation. And the curved path is like this one. So if someone launch the object and then it naturally going up and then eventually hit to the ground again. Then how we describe this curvilinear motion? The last time when we talk about rectilinear translational motion, which is straight the motion, we derived three kinematic equations of motion under the assumptions that acceleration is constant. So those equation was your velocity was your initial velocity plus the constant velocity time t, and then your position is your initial position and initial velocity time 1/2 and this one, and then your velocity square is initial velocity and then 2 and position difference. So these are three fundamental kinematics equations of motion when acceleration is constant. Then we apply this one to curvilinear motion. In a curvilinear motion, if you look at the position, because this is kind of curved motion, I want to represent position using this vector. So this is my r. So anyway, so the r represent from the origin here to the particle at a given time. So if we know the position r, okay, then if you take derivative of r with respect to time, that will be the velocity. So your velocity should be dr over dt of that object. And how about the acceleration? Acceleration is the velocity over dt. So the concept is exactly the same. Then what is r? Your r can be represented by component of x and I. Your component of x and component of y. That means since this is a vector, your vector can be broken into x component, right? And then your r can be broken y component like that. And then this rx, ry, okay, rx and ry is function of time, because as given time, the rx, ry position keep changing. That's why these are the function of time. So if I just write down like that, so your rx is function of time and I direction, and y is also function of time and j direction. So these are my r. So in order to get the velocity, if you take a derivatives of dr dt, then we just take derivatives of rx component, right, and I, and then y component of r and dt j. So we can simply notate this one is rx dot I, ry dot, let's omit the parentheses here, something like that. And how about the acceleration? The acceleration, if you take another derivatives here, this one should be the second derivatives of I, and second derivatives of y component of r, j, like that. So conceptually, this is curvilinear motion. However, once you break your position vector into x and y, then we can just take derivative x component, y component separately, and then it just go further if you get the acceleration. That means we apply these kinematic equations of motions to x and y component separately. That's the very important concept. I want to show you one example. So in this coordinate system, the object just moved, follow this kind of path. Then this particle just moved from the origin to a certain path following this curved path. Then we know that this curved is defined by this function y is equal to 1/2x squared. That's the curved path function. This is x, this is y. Let's say when this object reach at this position when x is 2 meters, this is curved path. So in a case, this is my r, this is my r. So my r position vector is rx ti ry tj, and then my rx is just x function, because x is just keep changing as a function of time. So let's say x is just a function of time, so just change x. But since we know that the motion is restricted by this curved path, once we know x, then you know what is r component. R component is 1/2 and x square j, right? Because whatever the x, the y is determined. Then if you want to know the velocity, you just take derivatives of r. Then means your x, you just take derivative of x, then you have to take a derivatives of your y components. So that's why if you do that, that is 1/2 2x, and then because of chain rule, you have to do another derivatives like that. Then what is x dot? 1 dot. So this is x component of velocity, right? So let's say at a given time when the object is on 2 meters on the x-axis, then at the time, for example, your x component velocity is 1 meter per second, for example. Then what is the velocity of in a case, this is your velocity. Okay, so your velocity is equal to your x component velocity was given as a 1, and then this is x is your position x, so this is 2 meters, and this is another velocity, so this is 1. So basically this is I plus 2j. So the velocity magnitude should be 1 square 2 square. So that's why this is square root of 5. So in this simple example, given x position and given x component of velocity, then your y position will be determined by the x positions. That's why if you apply, if you just put the y component using that curved path function, then by differentiating the r, you can get the velocity. Then you plug all the given information to this equation to get the velocity in this example. So in this plot. I already showed this plot. And here, let's say this object just move through this kind of curved path. So at this time, maybe it's just moving in this way. Then we know that you can break the position vector into x and y. That means we can analyze the motion of my curved path by breaking the motion into x directional motion and y directional motion. Right? So this curved path, let's say the ball is kind of moved in this way. So this is kind of combinations of from here to here, plus this one is going up and going, and then this is going up and down. So if you just add this one, you can generate this kind of motion. That means while the object moved from here to here, this is purely x directional motion, and then if the object is going up and down, this is purely y component motion. So I can say this is x component motion and this is y component motion. Then, as I said, in particularly in this projectile motion, let's say this is ground and you launch the ball like that. After the ball is released from your hand, there might be there's no acceleration along the x direction, right? But in the y component, in the y directional motion, because of gravitational acceleration is always exist, so there's always accelerations which is constant. But right now the up is our positive, on the right side is positives, so acceleration is negative g. Okay, so let me just break down here. So let's apply the equations, the kinematic equations of motion on here. Let's assume that when you launch the ball, you initially launch the ball with initial velocity v0 and with an inclined angle which is theta. Then your x directional initial velocity will be the v0 cosine theta, and then your initial velocity along the y will be v0 sine theta. Then if you apply this kind of information to what should be my y directional velocity, so y directional velocity is equal to y directional initial velocity plus ACT, but our AC is negative g, so negative GT. So that's why we got minus GT. How about the position of y? So my y is equal to my initial, the position of y, and plus y directional initial velocity t, and minus 1 over 2 g t squared. How about the x component motion? My x component velocity x is equal to my x component of initial velocity and plus ACT, but right now there's no acceleration, so this is g and time t, so there should be 0. So you know that along the x directional velocity is always conserved unless you apply additional force along the x direction. And x directional position x is equal to initial position of x and then initial velocity and t, and 1 over 2 0 t squared. So that should be 0. So this is a 0 and this is 0. So basically we have this equation. So from now on, you know that for curvilinear motion at any given time, if you want to get the position, get the position r, so your position r is equal to, if I just rewrite this one, xo and vo xt, okay, this is in my xi, and then y naught and vo naught t 1 over 2 gt j, right? That's my position. How about velocity? The velocity is the v naught x I and v naught y minus gt 0, because these are all x component, okay, and these are all y component. Let me talk to one more things, which is about relative motion. Relative motion concept is pretty simple. So let's say your object A is kind of following this kind of curved path. Then you have another object like B, and B kind of moved along this kind of path. So B is moving that way, and A is moving that way, for example, like that. Then your position of R should be RA, and then position of B object is just RB, like that. Then let's say this is my X, this is Y. Then what if you want to get the velocity of A with respect to B, not with respect to your origin O? I know that if you want to get the velocity of A, velocity of B with respect to O, the velocity of A will be just take derivatives of R dt, and VB is just take a derivatives of RB over dt. That's it, right? But right now, I want to know, let's say you are standing on top of the B. I want to know the velocity of A with respect to yourself. That means I want to know the velocity of A, okay, with respect to your B. So this should be not the same as A. So this is not the same. So in order to do that, you have to take derivatives of R relative to B and dt. So what is this one? So R A relative to B is just RA minus RB factor, right? Because if you look at this one, if you look at this vector, this vector is RA with respect to B. So because if you add RB plus RA with respect to B, that becomes RA. So your RAB is equal to RA minus RB. So your relative velocity of A with respect to B is just take a derivatives of this one. That means if you know the velocity with respect to origin, then you can just subtract these two. So that's it. So this is called the relative motion analysis, the relative velocity, because the velocity of A is determined or expressed by another moving object, which is B. So that's why this is called relative velocity, and this is called relative position.